Hey, Katie.
Hi, Ben.
So, I've been hearing this term big data, and I don't really know what it means.
Oh, well, so your problem is you're supposed to put a hashtag out in front of it. It's called
Oh,
hashtag big data.
hashtag. Is that a thing?
Yeah, that's the real name.
All right. Well, let's talk a little bit about data, big data, kind of the difference, and how big is big data. I don't know. I feel strange saying that, but you are listening to Linear Digressions. Okay, so I guess we'll start with some projects that we've been talking about over the last many episodes. So way back when you were talking about writing an detector because we had a lot of ums when we were recording our podcast, and you had to go through and remove all of the ums. And one of the problems you were running into, if I'm remembering correctly, is that you were dealing with a massive number of features, and also the ums might not be necessarily the same length, so they might be different features, different numbers of features.
So to unpack that a little bit, so the sampling rate for these microphones is 44 kilohertz, so that's 44,000 measurements per second.
44.1 kilohertz or 48 kilohertz. Sorry, I'm an audio geek.
Wait, how is it 44.1 or 48?
Well, so actually the microphones, going into geeky digressions audio world, most microphones you can sample as fast as you want. The microphones themselves don't actually determine the sample rate. This is actually an exception because we're using the Blue Yeti microphones, and those plug in with USB, and they've got their own little chip inside of the microphone. But the sample rates that you'll most often find are 44.1 kilohertz, 48 kilohertz, 96 kilohertz, which you don't see as often. Or if you go to like a recording studio, that's 192 kilohertz oftentimes they'll record in. And what that means is, let's take 48 kilohertz instead of 44.1, because actually the main reason 44.1 exists and is widely used is because that's what CDs use. But 48 kilohertz means that we are taking a measurement of the position of the diaphragm of the microphone 48,000 times per second. And because we're doing it so fast, we're actually able to kind of create a reproduction of the movement of the microphone diaphragm. And then when we take that and we pipe it into a speaker and we tell the speaker to move the diaphragm and its diaphragm in the same way, then it actually reproduces a pretty good approximation of sound. And that's how that all works. So when you have 48,000 samples per second, and we're talking about data, that's 48,000 data points every second. That's a lot of features to take into account when you're trying to detect something like an or do speech recognition or whatever it is.
Yeah, and so usually when we record, let's say for a typical episode, it's usually we have more raw material and then kind of edit it down, but sort of that full uncompressed raw size is usually a couple hundred megs, I think.
Yeah, and actually, if you try and figure out how many samples there are in, let's say, a 20-minute episode, and there may actually even be more than that because we record a little bit longer and cut it down for everyone's benefit. But that's 20 minutes times 60 seconds times 48,000. I just did the math. That's 57.6 million data points in a 20-minute episode of Linear Digressions.
Good math. And so then we edit it and we convert it from the MPEG format to the MP3. Is that the right
yeah.
Or
yeah.
no, from AIF to MP3.
Sorry, AIF, yeah. AIF is totally uncompressed. MP3 is fairly well compressed. It could be 1/10 the size. And that's what allows you to download it rather than being so huge. It's actually a manageable size for you to download on your computer or your phone, or even a 3G connection if you needed to.
Yeah, I think
and that's with data. That's data compression right there. So it's taking out all of the stuff that you wouldn't notice if it was gone, and it's basically removing it or encoding it.
Yeah, and I think that compression stuff from AIF to MP3 takes it down by roughly an order of magnitude. So that'll take us from maybe 200 to 20 or so, and then, like you said, that's manageable.
Right.
Okay. So that is just from our little setup that we have here. But obviously when people are talking about big data, they're usually talking about big centralized places that lots of people are contributing data to. or that potentially the data itself is very large. So I guess we should split it into two types of big data. So one is maybe something like Twitter or YouTube, where you have lots and lots of people who are uploading, all of them are creating data, generating data, and then uploading it to sort of this big network. And so each one of those files might be not ridiculously large, like maybe
like a tweet is going to be not very big.
Right. I think tweets are, once you include all the metadata, I read that tweets are something like 3 kilobytes a piece. And then videos obviously can range a whole lot in how big they are. And then there's also kind of the scientific big data. And so for these, I'm thinking about things like particle physics experiments, which is something, of course, that I know very well. Also, astronomy has some ridiculously big data experiments that are sort of in construction right now. And I'm also thinking about genomic data, which is still kind of really ramping up. It's still fairly expensive to do things like genomic sequencing, and there's the data sets don't always necessarily have huge numbers of rows in them. But each one of those rows can be really, really big in terms of the amount of data that you need to have in it to do something like a full genome sequencing or analysis of full genomes.
Right. So I guess then putting all of this into perspective, like to my feeble human brain, 57.6 million data points seems like a lot. But really, in perspective, that's very, very small compared to some of the experiments that are being run, some of the data sources that are constantly being contributed to, like Twitter or whatever it is. 57.6 million is just change. It's nothing.
Yeah, so let's attach some numbers to this. I'm reading this paper. It's called Big Data, Astronomical or Genomical, ? And we'll post a link to this in the show notes. And so they were comparing actually these 4 types of big data. They look at astronomy big data, genomics big data, Twitter, and YouTube. And so to attach some actual numbers to the things that they were talking about. So the first is, let's take astronomy. And one of the big players in astronomy is the Australian Square Kilometre Array Pathfinder project.
Okay, yeah.
And that is, it looks like currently up and running, and they say that it's currently collecting 7.5 terabytes per second of image data.
Wait, per
that is
second?
Insane. Yeah, that's
per
what it
second?
says.
Okay, 7. Whoa.
That's nuts.
Okay, so yeah, let's put that into perspective and compare it to, I guess, our example with the episode of linear digressions. Like I said, that was 57.6 million data points. If you divide that by 8, then you'll get the number of bytes, and this is uncompressed. This is like biggest possible case for an episode of linear, a 20-minute episode of linear digressions would be 7,200,000, so 7.2 megabytes, and we're talking about terabytes. So about 7.5 megabytes versus 7.5 terabytes. The difference between that is 6 orders of magnitude, 10 to the 6th versus 10 to the 12th. So
Factor
that's
of a million. Yeah,
a million times, right?
Yeah, this is nuts.
And that's per second.
And that's per second. That's not even the full capacity of this thing. So it's running at that rate right now. And it looks like the projection is for it to increase by another factor of 100 in the next decade or so to 750 terabytes per second, 25 zettabytes per year. I don't even know what a zettabyte is.
Oh, I can tell you in a second. First, I just want to give one more number, which is that 7.5 terabytes would fill up pretty much an 8 terabyte hard drive, which is pretty much the biggest hard drive you can buy these days. That's about $200. And that's not even taking into account how the heck you get all that data onto, like, how do you capture all of that, right? So what was the thing you said, zettabytes?
Yeah, they say by 2025, the projected data collection from this telescope is 25 zettabytes per year.
All right, that is 10 to the 21. So going up the, what is this called? The decimal unit prefix tree, right? You've got 10 to the 1 is deca, and then hecta, and then kila is 10 to the 3. 10 to the 6 is mega, 10 to the 9 is giga, 10 to the 12 is tera, there's the terabyte. 10 to the 15 is peta,
Okay.
And then 10 to the 18 is exabyte.
Okay.
And then 10 to the 21 is zettabyte right there.
Oh, wow. Okay, so
And that term, by the way,
Uh-huh.
didn't even reach adoption until 1991. So like back in the 70s when they came up with peta and exa and started adopting that, I mean, no one could even imagine that we would ever need to use a term above that.
We have to make up words for how much
We just
data
made up
we
a
have.
word, yeah. There's also right above that, that's 10 to the 21 is zettabyte or zetta, and 10 to the 24 is yada, which really sounds like a joke.
Well,
Yada,
we'll,
yada,
we'll
yada.
get there someday.
Yeah.
Okay, so astronomy. Completely insane amounts of data.
Right.
Moving on, YouTube. So YouTube, it looks like the current numbers are something like, it's about 300 hours of video that are uploaded every minute.
300 hours per minute.
So you're just never going to catch up with all of YouTube. And then extrapolating out, we'll say in the next 8 years, 6, 7, 8, well, how many years is it till 2020? Oh my God.
9 years.
Okay, 9 years.
It's 2016
Ooh,
right now.
Yeah. The next 9 years, they expect that it might be something like 1,000 hours to 1,700 hours per minute. So that would be 1 to 2 exabytes of data. So exa is one level below zetta.
Zetta,
right?
yeah.
Okay, so we're talking a factor of 1,000 to 10,000 less than the astronomy from
So
YouTube.
astronomy still wins over YouTube.
Yeah, by a factor of 10,000.
That's
By
crazy.
a lot.
That's just crazy.
It is bananas how much data comes out of these scientific experiments, and I think that particle physics is well, we can come back to this at the end. Particle physics, just to put it in context, is running a little bit behind. I think that the LHC data output is something like 30 petabytes per year right now, although that's right now as opposed to in 9 years. But I will say this is that when we were working on the LHC, there's a vast amount of work that goes into actually selectively throwing away data. This is called the trigger. And so
Yeah, I was just going to say, like, you don't necessarily, you said that particle physics is running a little bit behind, but really you don't want to be generating that much data because it's really expensive and it's also really, really difficult. Like, how do you build something that can capture that amount of data per second and then also store it and then also be able to do analysis on it? That's just... It's really hard.
Yeah, so the calculation that physics made is basically we're going to have very intense like streaming data capacity that does a lot of our analysis sort of on the fly. And then only the most interesting things get written to tape, and then those are written to disk, I guess now. And those are the things that somebody like me has to go through and actually analyze. And so just to put this in perspective, there's something like 40 million bunch crossings per second at the LHC. And the trigger will take it down to something like 200 bunch crossings per second that actually get recorded. So from whatever that reduction factor is, I can't do it in my head right now, but 40 million to 200, that's the data reduction that we have that gets us to 30 petabytes, a very slender 30 petabytes per year.
Oh my gosh. That's
Anyway,
crazy.
Yeah, it's pretty nuts. Twitter, as we were sort of speculating, Twitter is, we think of it as big data, but it's kind of the lightweight of the group. So something like 500 million tweets per day are generated through the Twitter network. And as we said, each was about 3 kilobytes. And Twitter is plateauing a little bit, maybe compared to some of these other data generating processes. But let's say they grow by a factor of 2.5 between now and 2025. So that puts them at 1.2 billion tweets per day. That's about 1.3 petabytes per year. So that is a full factor of 1,000 less than what we're talking about from YouTube, and then YouTube is a factor of 10,000 below what we're getting from astronomy.
This stuff is really, really hard to conceptualize. I mean, that's 1,000 times less, and yet just a petabyte of data is more than you would ever have in your household, by a lot.
So,
I mean, maybe if you're an unusual person.
Well, but so here's let's get weird with this for a second.
Okay.
So we've talked about astronomy, we've talked about YouTube, we talked about Twitter. There was a fourth one that we were going to talk about, and that is genomics. And so the reason that I got a little bit squishy when you started talking about how people don't have this much data in their house is you have vast amounts of information that's stored in your cells in the DNA. So if you think of your DNA, there's about 3 billion base pairs in the 23 chromosomes.
3 billion, you said?
Yeah. Uh-huh.
Okay.
So not exactly 3 gigabytes of information, but like if you make the
it would be 3 billion over 8, yeah.
Yeah, so you can make kind of like the quick hand wavy approximation that so there's 4 types of sort of base, I'm losing the word at the moment, but like T, C, G, and A, right? Like the
right.
fundamental units of DNA.
Your
like the base pairs or something?
Yeah.
But there's 4 of them, and so you can say that each one of them takes like 2 bits to represent, basically, like ones and zeros. So if you have 3 billion base pairs, and then each base pair is 2 bits of information, then you can get 4 base pairs per byte. And so what's 3 billion divided by 4? It'd be like 0.75 billion, 750 million.
Let's say a billion. That's easier.
Okay, we'll say it's a billion.
It's a gigabyte of data.
It's a gigabyte of data per cell.
Cell. Right.
And then I just had to Google this. How many cells are in your body? These are numbers that I don't know, but I will share them with you now. So this is one of those things that's also kind of hard to estimate. But somebody went in and kind of did a back of the envelope thing, and the number they came up with was about 37 trillion cells. So what's a gigabyte times 37 trillion? How many bytes is that of information in your body?
Oh, okay. So 37 trillion times. Oh, so we can just use our little tree for this, actually. We could say 10 to the 12th is a trillion. Mm-hmm. 10 to the 9th is a billion. Mm-hmm. And if we add 9 plus 12, we get 21. That's a zettabyte. So some number of zettabytes. Oh, so there we are.
A zettabyte of data in your body?
What was the number? 37 trillion, you said?
Oh, yeah.
So we'll say 37 zettabytes.
So actually do have a lot of data in your house, as it turns out. It's walking around and listening to this podcast right now.
Thank God we didn't have to buy hard drives. I don't know. We're born and happen to have all that data. That's lucky us.
Yeah, our body seems to be pretty good at like packing it in.
Now, a lot of it I'm sure a lot of it's quite redundant, wouldn't you say?
Yes. And so if you're going to do something like sequence a genome, you have 3 billion base pairs, and you say that like they're going to be mostly the same throughout all the different cells. There's important caveats to that, which we should get to in a second. But It turns out that doing genomic analysis and sequencing and alignment is pretty difficult. It can be a little bit noisy. And so one of the sources that I was reading says that in order to get those 3 billion base pairs correct, you want to collect roughly 30 times as much data as that. So that would be 100 billion base pairs for doing the sequencing. And so then once you start to figure out like how much data that is, it's fairly expensive still to do genomic sequencing. I think a full human genome, although it's come down an insane amount over the last decade or two, but a full human genome sequencing costs something like $1,000. And so it's not really accessible to most of the world right now, but there are 6 billion people, 7 maybe, walking around. And so you can imagine that if the cost continues to fall and there's sort of scientific push for it, that there's potentially hundreds of millions or even billions of people who could have their genome sequenced, each of them with potentially 100 billion base pairs that get collected. And so we're talking about not just very, very wide tables, but very, very long tables. And we are in an extraordinarily high data kind of regime between those two pushing factors. Doing kind of, again, the number crunching, it's really hard to extrapolate too far just because genomic sequencing is still so young that it's hard to know exactly how it's going to keep scaling. Like, do you assume that it keeps scaling at the rate that it's been scaling so far historically? Do you assume that it's going to scale like Moore's Law and so on, blah, 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 because you'll reach different conclusions depending on the assumptions that you make about the future performance of the field. But they make sort of an estimate that in 2025 for human genomes, we might need something like 2 to 40 exabytes. Where does that put us relative to the astronomy? Is that still below the astronomy right now?
That's still quite a bit below, yeah.
Okay. So it sounds like maybe astronomy is perhaps still winning.
So I just want to take a brief moment. Now that we've gone through all of that, I want to take a brief moment to just kind of talk about how we've been talking about terabytes and petabytes and exabytes and zettabytes kind of interchangeably. but the jump from any one of them to the next one is a factor of 1,000.
Yes.
That's just insane. Like, I can't even keep in my head what the number 1,000 means, right? I mean, the best I can imagine is like doing it with M&Ms or something, 1 M&M versus 1,000 M&M or something. But it's just the numbers that we're talking about, especially for astronomy, but really for any of these examples, are just gargantuan numbers.
Yeah, and it's not just the collection and the storage that comes attached to these numbers, but the reason that you're collecting all this data is because you want to be doing analytics on it. And I think that this is where genomics like really pulls away from the pack in some senses, because doing analytics on genomic data is really tough. You need to do things like alignment, which is where you actually take these strings of DNA, and then what you want to do is you want to put them in basically a matrix so that you can have each row be like a person in the matrix, and then the genes that are comparable across people are kind of sitting in the same places so you can compare them more directly. That alignment process is very, very difficult, and it's hard to get like consistent answers, and it's very computationally expensive. And so doing analysis of this genomic data is, it's extremely challenging now, and it's only going to get harder. And so there's a lot of people who I think are looking very carefully at like, well, we have all these ideas about what we want to do if we could collect all this genomic data, but do we have the computational capacity to deal with it? And of course, there's a lot of very smart people who are working on trying to make different types of like cloud computing platforms, basically, that can do genomic data storage and analysis and things like that. But yeah, it's going to be extremely challenging to keep up with the rate at which we could be collecting this data. And then the second thing I'll say is that we kind of brushed past this a little bit earlier, but how many base pairs do you really need to sequence per person? And if we say that a full genome has 3 billion base pairs in it, we're not really done there, because a lot of the reason that you're wanting to do this kind of science is because you're looking at, like, let's take the example of cancer, because I think that this is probably the single most like complicated case, but it's also one that I think is really driving this sort of research. So it's fair to take it as representative. Right.
You're not just looking at one cell and then taking a bunch of similar representative samples and combining that together. You're trying to compare healthy cells to cancerous cells or something like that.
Not just that, is that cancer is a disease of genetic variation. And so the cells that you find, let's say you have a tumor, and a lot of people have been doing research on just this topic. If you take cells from, like, let's say the middle of the tumor, those cells might have a certain mutation in them that allow them to do something like angiogenesis. So to build the blood vessels that supply the tumor with blood so that it can continue to grow. And that's a specific genetic mutation that you need to have for it to do that, build that like feeding network, if you will. But then you could also imagine that the tumors, the cells around the periphery, have a different mutation, and that mutation allows them to kind of break off from the main tumor and then go elsewhere in the body and metastasize the cancer. And so depending on where in the tumor you are, you can be looking at cells that have completely different sets of mutations. And this is one of the things that makes cancer so hard to treat, is that it's really hard to get all of it's not like everything in the tumor can just be hit in the same way. There's different mutations that are contributing on like a cell by cell basis. And so then you're looking at something like, oh, well, we would need to collect 100 or 1,000 times as much of the data to really get the full profile of all the different types of mutations we're dealing with here. So it only gets more complicated. So that's what's going on with #big data.
#big data.
Yeah. There's a lot out there. It's only going to get bigger.
Wow, that's seriously bigger than our undetector dreams.
Yes, I would say so. The world wouldn't be a very interesting place if an detector was the biggest problem we had to deal with.
That's a good point.
Yeah. It was very startling for me this weekend, kind of reading all of these papers and just realizing, like, I come from the LHC, I come from physics. I'm like, we're the biggest of the big data, and it's really quite humbling to think about how much data is coming even from next generation scientific experiments, but also, like I said, just that's stored inside of the cells that make up you and me and everybody else.
Linear Digressions is a Creative Commons endeavor.
which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.